And we have a cool video. Oh, see, look at that. That's still on the board. I'm so happy that's still on the board. Yeah, and someone colored in the heart. That's so touching, right? So, um, so we're going to talk about chemical bonding today, and it's just basically an extension of what we talked about last week, right? So there's this thing called the law of the conservation of mass, right? And what that means is that there won't be any change in the total mass of a reaction once the reaction occurs, right? So you put sodium chloride together and you make salt, table salt, right? And you have like some grams of sodium, some grams of chloride, and you put them together and they make table salt, you'll still have the same number of grams of each one, right? Okay. And so that's what the law of conservation of mass is. There's no detectable change during a chemical reaction. If the total mass involved in the reaction is precisely measured before the reaction, there will be no difference. And this was actually discovered by a guy named Lavoisier, which we mentioned him before, a Frenchman, Frenchman, Antoine Lavoisier, in 1774, right before our independence. How interesting is that, right? So, first question for today, right? First question for today. I, I'm thinking there's going to be a mad rush for people trying to get these questions correct before the end of the semester. uh, which of the following is true? Oh, I meant to say not true. Which of the following is not true? Put the not part in there, right? Um, about the law of the conservation of mass. There is no detectable change in the total mass. If the total mass involved is precisely measured, there is no difference. It was discovered in 1774 by Max Planck, right? Or all of these are true. What do you think the answer is? C, yes, the answer is quite literally Max Planck. He did not discover this. So the next picture we have here is just a demonstration of what's happening with the law of conservation of mass, right? When you have, for example, a reaction occurring, this is a wick of a candle and it's being burned, right? So there's oxygen inside this little bulb here and it's burning the candle. And as you can see, as the candle burns, and it's hard to tell, but there's just a little bit of smoke right there, and then there's a lot of smoke right here, right? It doesn't matter that you started the reaction over here and you're ending the reaction over here where the candle is about to blow out. You still have the same mass, right? You still have the same mass. Okay, so a question I might ask you on an exam, I would show you, for example, a picture like this or something not like maybe something that's like this but wrong, and be like, what is this not a example of, right? Or what does this violate? So if you see a picture like this, and then you see the scale's kind of up and not straight, not balanced, then it's violating the law of conservation of mass, something like that, right? Or if you see it just balanced, then it's not violating it. So the law of conservation of mass takes us to this thing here called the law of definite proportions. Okay. And what the law of definite proportions say is that it's just like when you're baking, right? It's not so much like when you're cooking, because in cooking you can just kind of throw shit together, throw stuff together and it will still taste good, right? You don't have to really measure things out. In fact, things taste better when you don't measure things out, I think. Um, like when I'm smoking a brisket, I just kind of I very liberally add on dry rub, and very liberally, it says it's going to be like an hour for every pound of meat, but I really do like 2 hours for every half pound of meat type of thing. Well, that means the same thing. Whatever. The point is, when you're cooking, it's not quite as precise, but when you're baking, you have to get the numbers exactly correct when you're baking, right? You have to have exact number of flour, the exact number of baking powder, baking soda, or the thing won't, the thing won't rise, the cake won't rise, for example. Same thing in chemistry here when it comes to the law of definite proportions. You have to have a certain number of copper to add with a certain amount of sulfur to get exactly the right amount of copper sulfide, copper 2 sulfide, right? So notice here, 10 grams of copper added to 5.06 grams of sulfur makes 15.06 grams of copper sulfide, right? So that's the law of definite proportions. And the reason why that's called the law of definite proportions is because when you put too much sulfur in there, right, you'll end up getting what you're going to get, right, which is the 15.06 grams of sulfur, copper sulfide rather, but you're also still going to get an excess of sulfur that wasn't used in the reaction, right? And for a cake, that means it's not going to rise, right? So, that's the reason why baking is much more like chemistry than cooking is, right? Same thing down here, right? If you have twice as much copper as the amount of sulfur, right, you're going to end up with a whole bunch of extra copper, an extra 10 grams of copper, because whatever is in the least amount will be the limiting part, and then it will dictate how much of the actual product you get, right? So again, if you have the wrong proportion of flour to baking soda, right, you'll end up with too much flour, and then what's going to happen is your cake won't rise. Does that make sense, right? So you have to make sure that the proportions are correct in baking, and it's the same way as it is in chemistry. Okay? So um, we've already talked about Dalton before. Dalton discovered a whole bunch of different elements, right? But he also, all these like old school chemists, they came up with so many different like the theories, hypotheses. I mean, I think they were just a whole bunch smarter than we were back, like, or maybe they just didn't have a lot of stuff to do, so they spent a lot of time thinking. The point is, though, Dalton here, he actually came up with some hypotheses to describe both the law of conservation of mass and the law of definite proportions. And these are the three hypotheses right here. Okay? Here are the three hypotheses, right? Each element is composed of small divisible particles known as atoms, which we already knew that before, right? We talked about that last week. Okay? So what that means then is that atoms are identical for the elements, but different from other atoms. Okay, again, we've already done that last week, so you should already know that one. The next one, the next hypothesis he came up with was that a chemical combination is simply the bonding of a definite number of atoms to make one molecule of compound. So this is the one that actually applies to what we're talking about today, which is the law of conservation of mass, right? A chemical combination is simply the bonding of a definite number of atoms to make one molecule of a compound, right? So a given compound always has the same relative numbers of each type of the atoms, right? An atom of sodium chloride, not atom, sorry, a molecule of sodium chloride will be the same sodium chloride wherever you find it. Does that make sense? Right? It doesn't matter where it came from. Then no atoms are gained, lost, or changed in the identity during a chemical reaction. They're just rearranged to produce new substances, right? So again, sodium doesn't change, right? You don't lose the sodium. You don't lose a chloride. What happened was it came together, rearranged itself to become sodium chloride, right? So that's the law of mass conservation and the theories or the hypotheses that Dalton came up with to describe those things. Okay. So just a little bit more about this. Over the years, more and more supporting evidence for Dalton's concept of the atom accumulated. Although there have been many modifications to his basic ideas, they have worked so well and for so long that we now call them the atomic theory, right? So a theory is a statement of science that has been tested over and over and over again based on true and proven hypotheses, right? And it's been so long, and nothing has ever, thus far, nothing has challenged it, right? And so that's when we can call it a theory. And so this is called Dalton's atomic theory, which is the cornerstone of modern chemistry, right? The cornerstone of modern chemistry. Okay, so here's your next question. Which of the following is not true about Dalton's atomic theory? Okay, which of the following is not true about Dalton's atomic theory? Okay, each element is composed of a small indivisible particles called atoms. That sounds reasonable. Chemical combination is simply the bonding of definite number of atoms to make one molecule of compound, right? No atoms are gained, lost, or changed in identity during a chemical reaction. They are just rearranged to make new substances, or all these things are true. All these things are true. Oh, wow, look at that. Somehow, which I kind of predicted this, right? Everybody got that right. Very good job. The answer is indeed D, right? But the people that usually answer wrong on purpose aren't here right now, so maybe that's why everybody got that right. So, good job, everyone. Good job. Good job. All right, so we've seen this already before, right? We've seen this slide before, and it comes into play again. Because remember what I said last week, right? The reason why any compound is formed from any two elements is because they all want to get the noble gas configuration, which means that they have 8 electrons on the outside shell, except for helium, it just needs 2, but everything else is 8 electrons on their outside shell, right? And that's called the octet rule, kind of like octopus, but octet, right? And so here's some formal definitions for, and just recall too, remember that, sodium will give up a single electron right here to give it to chlorine so that it has 8 on the outside with sodium, and then sodium will also have 8 here, because remember, chlorine will it'll take electrons from a kitten, right? So here's some general rules for the octet rule, which we've talked about before, so it should be a little bit of a review. Okay, valence electrons are the ones involved in compound formation, right? And having 8 electrons in the outer shell is very stable, right? And of course, the most stable of them all are the noble gases. So in forming compounds, atoms tend to either gain, lose, or share valence electrons to achieve a configuration that has 8 electrons in their outer shell, right? The only exception is hydrogen, because it only has 2. Which makes sense, right? Because on the periodic table, it only has 1 there. It only needs 1 more electron to get full, like helium. Okay? So the name of the game here is 8 electrons. Get them any way you can. Okay? So that being said then, right? That being said, there are a couple of things to note. Oh, I already told you about this before. Here, did I post this on Blackboard yet? Yes, I did. Okay, just making sure I posted that. I thought I forgot for some reason. Sometimes I forget the Wednesday lab. So anyway, and I've already said this before, right? Atoms that are the noble gases, right? They already have 8, right? So they don't really need to do anything. But other atoms, like chlorine and sodium, for example, they can only get 8 by gaining or losing electrons through transferring them or by sharing electrons, okay? Bonding by transfer of electrons is called ionic bonding, right? And we're going to start talking about that now. We're going to talk about some ionic bonding right now. Okay? Ionic bonding right now. I'm going to give you a chance to write that down, even though it's on Blackboard, but that's okay. Okay, so some things about ionic bonding, right? Which is transferring of electrons, that's gaining or losing electrons, right? In the transfer of electrons, 1 or more atoms lose their valence electrons, while another 1 or more atoms will gain the same electrons from the previous atoms, okay? So they do this in order to achieve a noble gas configuration, which is 8 electrons on the outside, right? They have this hole in their heart and they're trying to fill it with an electron, right? And that hole in their heart, if it gets filled, makes them a noble gas, right? It makes them a noble gas. Okay. So compounds that do this, right? They transfer electrons by either gaining or losing valence electrons through ionic bonding. Those are called ionic compounds, right? And they're called ionic compounds because when they lose or gain these electrons, they become these things that we call ions, right? And we're going to talk about these ions now. Okay? So here are ions, right? An ion is formed due to the loss or gain of electrons, and that destroys the electrical neutrality of the atom and produces a net negative or net positive electric charge. Okay? This net electric charge of an ion is a number of protons minus a number of electrons, right? So this is the part you need to remember. Metals tend to lose 1 or 2 electrons, okay? And then nonmetals tend to gain 1 or 2 electrons, or however many they need. Okay? That's the important part right here. Metals tend to lose 1 or 2 electrons. Nonmetals tend to gain electrons. So a test question I might ask you, is I'll name either a metal or a nonmetal, right? And you'll need to tell me whether or not they're going to tend to lose electrons, gain electrons, or just be, not do anything at all. And if it doesn't do anything at all, what is it? It's a noble gas. This is your next question. Ionic bonding results in what type of, in what ionic bonding is the result of what in regards to electrons, right? Is it the result of the sharing of electrons, the transferring of electrons, the excitation of electrons, or the promotion of electrons? Okay. Do 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 do. Do 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 do. Do 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 do. Well, that's just freaking amazing. Once again, every single person answered correctly. Good job. The answer is in fact B. It's the transferring of electrons. Anyway, so here's a happy little picture that's very helpful, right? Because it's a picture of the periodic table, and on this picture of the periodic table here, right, we have metals on this side, right? And look what they do. They tend to lose valence electrons, right? And then on the other side here, we have the nonmetals, right? It's all these purple guys right here that are labeled. And what they do is they tend to gain electrons, right? And so, for example, chlorine here, right, was neutral before, but likes to gain a single electron, sometimes from chloride, right? And when it does that, when it gains that single electron, what does it become? Negative, right? Because electrons are negative. And since sodium lost that electron, now it's no longer neutral, it's positive because it lost an electron, right? Because a minus cancels out a positive. Does that make sense? Right? A negative charge cancels out a positive charge. Okay. Everybody clear on that? I mean, it's a pretty helpful picture here, right? If you take a picture of this thing with your mind, right? Well, not even this part down here, just oops, not even this part down here, but just this part right here, the red letters, the red words, and just paste it in your mind like a AR type of thing, augmented reality on that periodic table. You'll do great. You will do great, right? All right, all right. So, how many electrons do they lose? How many electrons do they lose? Well, it depends on the group that they're in, right? There's a reason why the periodic table is laid out the way it is, and there are numbers there that are there. And the reason is this. Notice here the alkali metals here are all in group 1, right? And what happens? They lose 1 electron, becoming a +1 charge, right? The metals here, the alkali earth metals that are in group 2, right? Look, they have a +2 here because they lose 2 electrons. So quite literally, the group that they're in tells you how many electrons they're going to lose. Does that make sense? Right? Jump onto the other side where the nonmetals are, right? At group 7 right here, right? It's got a -1 charge because it's gaining an extra electron, right? And then group 6 here, gaining 2 electrons. That's why it's a -2 charge. Group 5, gaining a -3 charge, right? Because it's group 5. I mean, what's the pattern? Well, 7 plus 1 is what? 8, right? 6 plus 2 is what? 8, right? 5 plus 3 is what? 8, right? So literally every one of these atoms are trying to do what? Get to 8, right? They're trying to get to 8, okay? And then the one in the middle that's not actually listed, group 4, is 4, right? It's group 4, so it's 4, okay? And so again, what are these guys over here? Noble gases, right? So they're not going to interact with anybody. So what number should be up here? Exactly, 0. Dang, you guys are quick today. Man, I was feeling a little slow myself, but you guys are quick today. Everybody clear on that? It's simple stuff, right? Simple stuff. Okay, so let's talk about sodium chloride then, okay? I keep on using sodium chloride as the example because it's like the thing that everybody knows, right? Salt, okay? So here we go. We've got the sodium atom right here, right? As it is on the periodic table. It still has the extra electron, okay? And here we have the chlorine atom as it is on the periodic table. and it still has 7 electrons, right? So what happens is that sodium will want to lose that electron, right? Making it so now no longer it has 11 electrons to balance itself out. Now only has 10 electrons, right? And so that's why it's going to be a +1 charge because it's lost this electron. Guess who picks up that electron? Chlorine does, right? Because chlorine needs that electron, right? And so now chlorine, this electron right here, is this electron that just came from sodium. And so now, since chlorine has an extra electron, it changes its name to chloride and has a negative charge of -18, right? Because it got an extra electron, right? And again, this is the total number of electrons and protons, not the valence, right? They're just showing you the mass change. So notice, right, one more time, we have sodium loses an electron right here. So it's down 1 electron, so it's -10, right? So it's got a +1 charge, right? This electron comes over, gives itself over to chlorine. Chlorine becomes chloride, and now it has a -1 charge, okay? And that's basically how we make sodium chloride, because if you take a look here, right? Take a look here, we have sodium, right? And chlorine. We put them together and we get sodium chloride, right? For every 1 sodium atom, there's 1 chlorine atom, right? And so interestingly enough, chlorine gas, I used to think that chlorine gas, or chlorine, the atom, was quite incestuous and would rather be with itself. But I guess if given the chance, it wants to pair up with somebody else instead of itself, right? Or its family, right? So uh, So here we have actually chlorine atoms splitting apart to become a part of the sodium atoms, giving you the sodium chloride crystals, right? So the NaCl, the formula unit of sodium chloride, is the smallest combination of ions that gives you the compound, right? It gives you the compound. And then so this is just a look at what it looks like microscopically when you look at it, right? It's actually a crystal. That's why when you look at sodium chloride, or salt under a microscope, or even under a magnifying glass, it looks like cubes, right? It looks like little cubes, and the reason why is because when they become sodium chloride molecules, they arrange themselves in this very arranged manner, right? Very crystalline structure, right? And here's a single formula unit of sodium chloride right here, and another formula unit, and another formula unit. It's kind of like when we were talking about the snowflakes, right? When we had water, hydrogen bonding to each other when they froze, and you would always get snowflakes that were the shape of a hexagon or 6-sided shapes. This is the same thing with this, right? Except now it's sodium chloride, and it always makes shapes that are cubes, right? It always makes shapes that are cubes. So the next thing I want to show you is a video of actually salt being made. And so I got to plug in the sound here. This is the video I was talking about last week that I wanted to show you guys. I don't know if this is going to work. We'll see how it goes. How do you turn up the volume? I don't know. Oh, no. No. There we go.
Sodium. Simple and 11 protons and 11 electrons, arranged in shells.
Okay, let's start that over. Okay, watch this video. This is great stuff. Oh, I forgot to press play this time.
Sodium. Simple Na. 11 protons and 11 electrons, arranged in shells as 2, 8, and 1. Sodium is an alkaline metal. Like all the elements of this group, it's desperate to get rid of that extra electron. Well, kind of quickly, I should see some essentially a silvery surface inside. Indeed, wow! It slices like cheese, but it's actually a soft metal. Teo's offered to put on one of his favorite sodium demonstrations. What happens when the pure element dumps its outer electron in a violent altercation with ordinary water? He insists we wait until nightfall, when the reaction will be most spectacular. Kids, another lethal element, chlorine, one of the halogens. The result, he claims, will be a tasty flavoring for a net full of popcorn. Isn't chlorine deadly poison? Absolutely. I mean, chlorine has been used as a poison gas in World War I. To be perfectly safe with these two deadly ingredients combined. I didn't say that. I said that after they're combined, the result is perfectly safe. The actual process of combining them is fraught with difficulties. Okay, and that's why we're dressed up like miners here. First, a hunk of sodium in a dry metal bowl. Then a jet of pure chlorine. Surprisingly, no explosion. Somehow, when these two bad boys of the periodic table come together, they calm down. At the atomic level, sodium, an alkali metal, had an electron it didn't want, and chlorine, a halogen, wants desperately to grab an electron. Once the handoff was complete, both atoms wound up with full shells, making them stable, and able to join together to form a crystal compound we can't live without. Sodium chloride, table salt. Now, I don't exactly see, like, pile of salt anywhere. And the salt, what's the one up in the smoke? That's it went in the popcorn. Tastes like salt. The good stuff. Fresh. Fresh salt. Freshest salt in Taylor's farm. Taylor's backyard reactions have given me a crucial insight. How elements come together to form compounds is all about electrons.
That was cool, right? I wanted to do this experiment here, but they were afraid that something like this would happen. So here's another video to watch.
This is one of my favorite experiments. Suppose you want some fresh salt. None of that stale old store-bought stuff. You want the fresh stuff. You gotta make it yourself. Well, how are you gonna do that? Salt is sodium chloride. Sodium is a metal that explodes on contact with water, and chlorine is a deadly poison gas. They actually used it in World War I as a poison gas. But if you take a bowl full of molten sodium and you blow pure chlorine gas into it, you get a fire, and the smoke coming out of that is pure salt. So we hung some popcorn over it, salt and popcorn with a nice fresh salt. And it worked great. We got some good shots we used in the magazine. Then it turns out the net started melting. It actually dropped the popcorn into the molten sodium. Sodium exploded. We got popcorn and sodium flying everywhere. That's really not such a bad thing. It tells you that science doesn't always go the way it's supposed to. It tells you why it's important to wear a face shield and have all the right safety equipment. And it made some really good shots that we could use also.
So they thought that was going to happen in here, and that's why they wouldn't let me do the experiment in here. So sadly, I had to settle for showing you a video of it, right? But yeah, that was crazy because it melted the net, and all the popcorn fell into the sodium, and everything just started exploding. Absolutely crazy, right? So here's your Here's your next question then. Here's your next question. What do elements in group 1A of the periodic table of the elements tend to do with their valence electrons? Do they lose one electron? Do they lose two electrons? They gains one electron? They gains two? Oh my god, that's terrible. That's terrible grammar. Excuse my English. I'm Asian. Um, gain one electron or gains two electrons? Oh, that makes sense. Gains one electron. Oh yeah, that is correct English. I'm so proud of myself. I'm surprised you guys weren't more excited about that video because I was very excited to show you the video. So, what would you say?
I said, who was sitting there and was like, I'm going to mix this metal with a gas and eat it?
Well, think about it like this though. They don't actually use they don't actually do that to get salt now. Where do they get most of the salt that you eat? Say again? Yes, they mine it, right? Or they can get it from the ocean, right? They can take ocean water and they can evaporate the ocean water and it becomes sea salt, right? It becomes sea salt. It becomes sea salt. All right, still waiting for two more responses. Dos more responses. Okay, everybody's there. Okay, so this one wasn't quite as definitive, but most of you got this one right. The answer is indeed A, right? Because that, remember, was the group 1 was this one here, which is the alkali metals, and sodium is an alkali metal. And remember what we saw in the video, right? Sodium gave up 1 electron, lost it to chlorine, right? And that's how we made salt. So yes, cool stuff. Cool beans is what I think, right? Cool beans. So we can draw these things so that we can see the difference between an atom, right, and an ion. And the way we do it is with this thing called the Lewis structure. Okay, a Lewis structure is the nucleus and the inner electrons of an atom are represented by the elemental symbol, and then the valence electrons are shown by dots. Okay, so for example, here's chlorine, the atom, right, on the periodic table. But then when chlorine receives that extra electron from sodium, this is what you get, right? 8 electrons and then a minus sign, right? So on the periodic table, when it's just chlorine by itself, not having gotten an electron from sodium yet, it's just got 7 electrons, consistent with it being a halogen, group 7. But then it gains an electron, so now it has 8 electrons around it, and now it has a negative charge. And then on the other side, right, sodium here, right, as it is on the periodic table, without having given up that electron yet, has a single electron in its outer shell, in its valence. And then when it gives up that electron, this electron right here came over here, gave it straight to chlorine, so it became chloride, right? Now sodium has no electrons in its outer shell, but it's got a positive charge, right? So the reason why this is a little counterintuitive to a lot of people is because you're told over and over and over again that nature wants to be neutral, right? Nature wants to have 0 charge, and wants to be neutral. And on the periodic table, most things are neutral, right? But it turns out elements are all different, right? And they all want different things. But the one thing that all elements want to have in common is they want to have the 8 electrons in their outer shell, right? And having those 8 electrons in their outer shell calms them down, just like you saw with sodium and chloride when it made salt, right? So in this case, being a neutral thing is not as good as having 8 shells. 8 shells? No, 8 electrons in your outer shell. Does that make sense? Right? So we can do this Lewis structure thing with all the elements of the product table. And the thing about it is that an example of a test question I might give you is I might ask you which of the following is the Lewis structure for the fluoride ion, right? And I'll have Lewis structures there, and you have to pick the one, right? But just remember that fluoride, right, is the same thing as chloride, except it's with fluorine. And when you have the "ide" at the end, it's got that extra electron that I got either from sodium or whatever, right? And so it would be this plus 1 electron and a minus sign, right? So let's take a look at this. Notice how here in group 1, right, hydrogen, lithium, sodium, and so on, all the way down, they all have a single electron out there, right, because they're in group 1, okay? And then I'm all parched and my tea isn't in here. Dang it. That's okay. And then in group 2, right, which has beryllium in it and magnesium, notice that it has 2 valence electrons. So don't forget about that either. Remember that the number of valence electrons is in the group number, right? It's in the group number, okay? And then and if you don't know what the group number is, I guess they could make it where those numbers are slightly bigger up there. Maybe I can go up there with a Sharpie and just write it up there for you in big letters. That would probably help. Or big numbers, as it were, right? So we get to group 3. This is boron and aluminum, and notice they have 3 in their outer shells with their Lewis structures. Group 4, carbon and silicon, 4. Nitrogen, right, has 5, and so does phosphorus, right? So it's in group 5. And then group 6, oxygen and sulfur, right? Sulfur stinks, by the way, if you didn't know that. And then fluorine here and chlorine here have 7, right? And then, of course, we have our noble gases here in group 8 that have all 8 electrons, except for which one? Helium, that just has 2, right? But for helium, that's a full outer shell, right? So he's happy the way he is, Okay. Any questions about that? It's pretty simple stuff so far, I think. All right. So let's talk about ions then. Remember that an ion occurs when an atom receives or gains an electron, right? That's called an ion because it either makes it positively charged or negatively charged. So we actually call those special things. When you have a positively charged ion, we call that a cation. So those are most of the metals, right? So when you give sodium's electron over to chlorine, sodium becomes a sodium cation, right? So just think of cat as being positive and being metals, right? Sodium cation, or I mean, I wonder what's a good analogy for, or a good way to remember that metals are in positive charges are cations. Oh, I said that chlorine would steal an electron from a cat, right? Right? That makes sense, right? So so chlorine would steal an electron from a sodium, and that's a cat ion. Get it? Get it? You sure? I don't hear any laughter here. I'm just there. We go. Okay, thank you, thank you. Okay, so I need I need some feedback on my jokes. I mean, if they're not hitting, then I need to know. Okay, I need to know that my jokes aren't hitting. Okay, but see, you'll remember that now. You'll remember that because I said that chlorine would steal electrons from kittens, but we'll have to change it to cats to make it work with cation, right? See, look, Osvaldo's writing that down. Look at that. That is that. Oh, my bad. Whatever. You should have just let that one go. You should have just yes. I'm writing it down. So, all right, and um, so elements that tend to lose electrons are metals, of course, and they're called cations, right? They have a positive charge equal to the number of valence electrons that gives them their 8 outer electron shell, right? And then on the other hand, if you are gaining electrons, you're called an anion, right? And anions are always negative because you're gaining electrons, right? They're generally the nonmetals, right? And then so elements that tend to gain electrons are nonmetals, right? So now it's got a negative charge on the nonmetal ion, right? But then it'll still have its valence shell full, okay? So what's a good way to remember that? Anion 8. I know anion minus, anion steal electrons from cats. No, that doesn't work either. Well, I can't think of a good one for anions, so just remember the one for cations, okay? All right. Good stuff, right? So just to look at this one more time, right here, this slide, right? So these charges that you see up here for each one of these groups, right, represents the anion you get, right, when you take an electron from the cations, right, from the cats, the kittens, right? When these guys over here, and you would think that the nonmetals would be soft, right, and the metals would be hard, and they wouldn't let their electrons be stolen by some soft nonmetals. But it turns out that the nonmetals rule this relationship, right? And they're just taking electrons. They're stealing the electrons. These nonmetals are stealing them from the metals, right? And it's very unfortunate, but that's the way it goes sometimes in relationships. Okay, give, take, give, take, give, take. Never, never give, give. Especially with these elements, right? And you can see here for some elements like nitrogen, they need more than one electron to be happy. God, so greedy, right? So greedy. Everybody in a relationship like that? It's terrible, right? It's the worst. Okay. And so when you get nitrogen bonding with like 3 sodiums or something, right? Dang, sodium is just talk about a swinger party there, like a menage a trois going on there with 3 of them together, right? God, nitrogen and phosphorus, so greedy, so greedy. Anyway, the numbers here again, just to reiterate, right? These charges are the charge of the atom when it becomes a anion on this side or cation on this side, and the easy one are the metals because they're just the same number as their group number, right? But then on this side, it's their number minus 8, right? Their group number minus 8, right? So 7 minus 8 is -1. 6 minus 8 is negative 2. 5 minus 8 is what? Negative 3. Does that make sense? Right? Like I said, some elements are more greedy than others. Okay? More greedy than others. All right, so are there patterns of charges? Right? Valence electrons are lost by metals and gained by nonmetals, generally to the extent necessary to acquire 8 electrons. Let's just flog this dead horse some more, right? Into the most outermost shell. Oh, okay, I get it. I see what's happening here. And so that is so that they can acquire electron configuration that is isoelectronic with a noble gas, right? So in Greek, iso means the same. So they're trying to get the same electron configuration as a noble gas, right? So for example, something like uh, aluminum plus 3 has the same electron configuration as neon, right? And then sulfur 2 minus has the same configuration as argon. And we can see this right here in this next slide, right? So notice, right? Notice, for example, we have aluminum, right? And if aluminum gives up these 3 electrons right here, right? If aluminum gives up these 3 electrons, notice that when it gives it up, it has a 2 and an 8 there, right? That's all that's left once it gives it up. So notice that also neon has a 2 and an 8 there, right? So when aluminum gives up its 3 electrons to some greedy nonmetal, right? It just takes, right? It becomes the same electron configuration, right? As what? Neon, the nearest noble gas, right? 2 and 8. So that's what it means to be isoelectronic. Does that make sense? Right? The same thing can happen here with sulfur. Sulfur will gain 2 electrons, another greedy one, right? It's going to gain 2 electrons, probably from like magnesium or something, or maybe 2 sodium sulfide. Man, that's 3 of them. That's definitely a menage right there. A menage with 2 twins. Interesting. Anyway, because it'd be 2 sodiums, so that'd be like twins, and then the sulfur. Anyway, so if it gains those 2 electrons, right? If it gains those 2 electrons, then it gets 8 right here in that last number instead of 6, right? And now it looks just like argon, its nearest noble gas, right? So the key thing to know about this is that the elements will go either backwards to the nearest noble gas, or it will go forwards to the nearest noble gas, right? To get the same electron configuration, right? As one of those noble gases. That makes sense? Yeah? 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 All right. Only a couple more slides here. A couple more. Okay. So what is an ionic bond? An ionic bond is an electrical force that holds ions together in a crystal lattice of the ionic compound. So remember I was talking about sodium chloride becoming a crystal, right? And when it comes to crystal, it's called crystal lattice. It's called a crystal lattice. Okay. And then in every ionic compound, the total charge in the formula always adds up to 0, and the compound exhibits electrical neutrality. So remember that I was telling you before, right? It was more important for a single atom to have 8 electrons than it was for it to be neutral. But guess what? When it combines with another atom, right, like sodium chloride, right, it has its 8 electrons. Both of them do. Chlorine and sodium do. But the other benefit is the fact that when they come together, they balance each other out and they become 0. So they're neutral just by the fact of them getting together, right? So it's like the best of both worlds. You get to take sodium's electrons, but then sodium gets to be neutral and it gets to have its 8 electrons, right? Does that make sense? Right? So I like that you're always like, because I need that. I really need that sometimes. It's like a comedy show, and you don't get any feedback from the audience. And so it's a good thing that there's somebody in the back just always thumbs upping me, because that's helpful. Thank you, Shanice. I really appreciate that. So shout out to Shanice back there. So anyway. I mean, I shout anybody out if they're thumbsing up me. So Osvaldo, thank you. Thank you. so, um, so yeah, the same thing is true here, right? We have oh man, see, calcium is also kind of greedy too. This time it needs two chlorines to be happy. So there's another menage happening right there. Two chlorines and a calcium, right? And but the thing is though, calcium has a +2 charge, remember, because calcium is over here in group 2 of the periodic table, and then chlorine has 1 minus charge, so it needs two chlorines, right, to balance out a +2 charge on the calcium. And then in the end, when they come together, there's 0 charge, right? So the best of both worlds, see? The best of both worlds. Okay? So we have these specific, so when we're talking about formulas for ionic compounds, right, you always want to have a 0 charge, right? And then all of the atoms have to have noble gas configuration, right, in their outer shells, right? Noble gas configuration in their outer shells, and noble gas configuration in their outer shells, and neutral charge. Okay, that's the goal. Okay, so I'm not going to make you write any like actual compounds out, but I will ask you to like look at some and see what's not charged correctly, right? Or what's not balanced correctly. Okay, but you're not going to have to like, I'm not going to give you a formula and you have to name it. I won't do that. Okay, so this is an example, right? But like again, I'm not going to make you write anything out, right? But for example, this is an interesting one here, right? So calcium has, again, I said it was group 2A or group 2, right? So it has a positive charge. And then there's another one called the phosphate ion, right? It's PO4, right? It comes like this. And I don't know if you knew this, but I wrote this up here. P loves O. That doesn't mean that Fong loves like somebody with the name O, right? No, that actually is phosphorus loves oxygen, is what that is, right? Does that make sense? And look here, we have a phosphorus, and look how many freaking oxygens it has. 4 of them. Talk about greedy, right? Man, unbelievable, unfreaking believable. Anyway, right? Anyway, so this guy here is already by itself with 4 oxygens, right? And it's still not happy, okay? It's still not happy because it still needs to have 3 calciums too to be happy, right? Unbelievable. Some of these elements, man, some of these elements, okay? So what's happening here is the fact that calcium, of course, has a +2 charge, like we already know, right, from the periodic table. And then phosphate here, with these 3 oxygens, because it loves oxygen so much, has a -3 charge. So when you put them together, you have to balance them out, right? So this is one of those things where you have to do the lowest common multiple, right? Because 2, right, here, the positive charge of 2 times 3 makes 6, right? And then the -3 right here times 2 phosphates makes -6. And that's how they're able to get their 0 charge. Does that make sense? I know that was a little bit crazy, and it took a long time for my last class to get that, right? So if it's a little confusing, I can say it again, right? If you have 3 calciums, right, the charge is multiplied by 3. Does that make sense? That makes it +6, okay? And then if you have the phosphate, the greedy phosphate ion right here, right? It's got a charge of already -3. So if you have 2 of them, right, you can multiply that by the charge and you get -6. So both of these now, calcium 3, that's +6, and then phosphate 2 -6 makes it so that it has a charge of 0. Does that make sense? So putting these two together takes a lot of work. So I'm surprised that they even work out. This relationship is bound for failure. Just so you know. Except that it's not bound for failure. That's the way they are, and they're always going to be that way. So we can call that like a toxic relationship, maybe. Okay. So here's a chart that helps you figure that kind of stuff out. Again, I'm not going to make you write these out. I'm going to ask you. I'll give you one, and you have to answer questions about it. Okay. So for example, if you have a metal that's a positive charge, right, and you have a non-metal that's a minus charge, it's just going to be a regular old MX, right? But say if you have a metal with a positive charge and a non-metal that has a -2 charge, it's M2X, which makes sense because you need 2 metals, both of them with a single plus charge each, to balance out the -2 charge of the X, right? So this example here for this would be like let's say oh sodium sodium which was a good one? Sodium sodium sulfide would work, right? So this would be like sodium sulfide, right? It would require 2 sodiums for every 1 sulfide. And again, think of this as like a menage a trois right here, right? With twins, okay? Got one guy here, 2 girls, right? And they're together. And that's what's going to make those 2 happy. Make sense? Right? Then if you have a -3 charge, super greedy, right? You need 3 metals to balance out the -3, right? And it's the so on, right? Now you're down here with 2 plus 2 charged metals, which is the alkali earth metals, right? So you need 2 of the non. I guess it's not always non-metals that are being greedy. Sometimes it's the metals, right? So the here, so if you have a +2 charged metal, you need 2 non-metals, right? Or if you get here, and now you have a -2 and a -2, then you just need 1 of each because -2 -2 cancel each other out. They are even, right? And then here's that one thing I was talking about before, where if you have like the phosphate ion, the calcium phosphate ion, you need 3 of them to balance out 2 of the phosphates because the phosphate had a -3, right? Times 2 makes -6, and then the metal like calcium had 2 times 3 is +6, and that actually balances it out there. And then this is just the opposite on the other side here, right? A metal was +3, like aluminum, for example, right? Needs 3 of those, so aluminum chloride, for example. And then the same thing, this is the same thing as this, except backwards. And then over here we have MX again, when you have 3 and 3 and MX again. So anybody have any questions about the way atoms come together, right? It's pretty simple that way, pretty simple. Okay, so the last slide I want to talk about today, is ionic compounds, and we'll jump into some other stuff on Wednesday, right? So, due to very strong attraction forces between oppositely charged ions, ionic compounds are always crystalline solids, and they also have a very high melting point and high boiling point, right? So, have you ever noticed that you can throw like salt onto a frying pan and like fry it up and it never melts? But you throw sugar onto a frying pan, it turns like brown and becomes caramel, right? Which is kind of funny because they look almost exactly alike on the outside, right? But they react very differently to heat. And I believe like I think that the melting point of salt is actually like 600 degrees Celsius, so it's pretty high, right? Uh, the boiling point of salt is even higher than that, right? But you compare that to things like sugar, like glucose or sucrose, and I mean that turns to caramel with just a little bit of heat, right? So that's the difference. We'll talk about that on Wednesday, where ionic compounds are actually very strong, right? Because opposites attract, okay? They attract strongly, and so they have very high melting points. The other kind of bond that we have is called the covalent bond, where they share electrons, but when they share electrons, it's not as strong, right? And so those have very low melting points, right? And sugar is a covalently bonded molecule, and when it's covalently bonded, it can melt very easily inside the frying pan, right? It doesn't take that much heat at all. Doesn't take that much heat at all. Okay, so ionic compounds have a very specific property, and an electric current is passed when an electric current is passed through them. So interestingly enough, if you have solid salt, like solid sodium chloride, and you try to put like 2 electrodes in there and try to make a light bulb light up, it won't do it, right? Um, when it's solid. And part of the reason why that is because you have those crystals, right, and they're touching each other, but they're not touching each other enough to actually to make a current, right? But then if you melt that salt, right, into like a molten salt, right, then it will definitely conduct electricity because now the molecules are much more closer to each other and they're touching each other much better, and it will conduct electricity. So this is a very special property when it comes to ionic compounds. When they're solid, they will not conduct electricity, right? Because the ions don't move. But then when they're melted, like into molten salt, right? Like a molten salt sculpture, right? They will conduct electricity. Okay? And then we'll talk more about that conducting of electricity on Wednesday. So thank you very much. And I will see you on Wednesday if you have lab on Wednesday.